Welcome to the 8th lecture of Module 1, which is Diffusion Mass Transfer. In this lecture, we will discuss the multi-component diffusions and diffusivity in solids and its application. So, before going to this lecture, we will have a brief summary on our previous discussion, where we have discussed on the diffusivity measurements and prediction. And in our previous class, we have considered gas phase diffusion coefficient prediction, gas phase diffusion coefficient prediction, and mainly we have discussed two empirical correlations, which is Fuller et al. Equations, and secondly we have considered Chapman and Enskog equation. Chapman and Enskog equation. These are the predictive method for gas phase diffusion coefficient prediction. And secondly, we have considered the liquid phase diffusion coefficient measurements, liquid phase diffusion coefficient measurements, and mainly we have considered a very simple method of diaphragm cell method. And the third thing, we have considered liquid phase diffusion coefficient prediction. Coefficient prediction. Here we have considered two well known correlations, Welke and Chang. And the other one is Stokes-Einstein relation. Now, in this lecture, we will discuss multi-component diffusion and diffusivity in solids. As you know, for multi-component diffusion, the system or the diffusivity for different components will affect on the other components. So, it is a bit complex problems to analyze multi-component diffusion. Complex problem, and diffusivity in solids is important, particularly for catalytic reactors. So, there are some other examples we will consider later when we will discuss the diffusivity in solids. Let us consider the multi-component diffusions. Although it is a bit complex problem, we can analyze these multi-component diffusions by using a Stephan-Maxwell method. Stephan Maxwell method. First we will consider for binary system, and then we will extend for the multi-component systems. For binary systems, following are the assumptions. The partial pressure difference minus delta P A is proportional to molar concentration of species A and the molar concentration of species B, C A and C B. And secondly, this delta P A is also proportional to the diffusion path length. So, if we consider delta x is the diffusion path length, so delta P A partial pressure difference should be proportional to delta x. And then third point is minus delta P A is proportional to the velocity difference between component A and B, that is V A minus V B. So, from this we can write at constant temperature and pressure, we can write minus delta P A is proportional to C A C B delta x V A minus V B. So, we can write minus delta P A is equal to K C A C B delta x into V A minus V B, where K is the proportionality constant. Now, if we take limit delta x tends to 0, we can write minus d P A dx will be equal to K C A C B V A minus V B. So, we can write minus d P A dx will be equal to K C A C B V A minus K C A C B V B, and we know that we can write C A V A is N A, C B V B is N B. So, this equation will reduce to K C B N A minus K C A N B. C A is equal to P A by R T, then the above relations will be minus R T d C A dx is equal to K C B N A minus K C A N B. If we give, this is equation number 8.1. So, we can write this is equation number 8.2. Now, we know that the total concentration C is equal to C A plus C B. So, we can write C B will be equal to C minus C A. So, if you substitute this in equation 8.2, it will be minus R T d C A dx is equal to K into C minus C A into N A minus K into C A N B. So, we can write this will be equal to K C N A minus K C A into N A plus N B, from where we can write N A is equal to N A plus N B into C A by C minus R T by K C d C A dx. Now, if we consider R T by K C is the DAB, the diffusivity, in that case this equation will reduce to N A is equal to N A plus N B C A by C minus DAB dCA dx. So, we can write this will be equal to N A plus N B Y A minus C into DAB DYA dx. This is equation number 8.3. So, this is the similar equation or identical equations with the identical equation with Fick's first law. Now, if we consider multi-component mixture, then this equation 8.2, we can write multi-component mixture so n components and secondly n minus 1 binary mixture. So, from contribution from all these binary pairs we will have to taken into account. So, this equation 8.2 for this multi-component mixture we can write as minus R T d C I dx will be equal to summation over j is equal to 1 to n, j not equal to I, k I j c j n I minus c I n j. So, now divides both sides by C and R T. So, from where we can write minus dy I dx would be equal to summation over j is equal to 1 to n, j not equal to I k I j divided by R T y j n I minus y I n j, which is equal to, we can write summation over j is equal to 1, j not equal to I to n 1 by C d I j. From the definition of diffusivity we can substitute y j n I minus y I n j. So, this is equation number 8.4. Now, this equation 8.3, this equation which we have obtained, this we can apply for multi-component mixture, and we can write Ni is equal to yi summation over j equal to 1 to n nj minus C d I mix dy I dx. This is equation number 8.5. Now, if we compare this to 8.4 and 8.5, then we can obtain this di mix, the mixture diffusivity. So, the mixture diffusivity di mix, we can write Ni minus yi ith components summation over j is equal to 1 to n nj divided by summation over j is equal to 1 to n, j not equal to I 1 by d I j binary diffusivity into y j n I minus y I n j. So, this is 8.6. So, this is the mixture diffusivity. Now, if we consider the special case, only ith component diffusing, all other component non-diffusing. So, nj will be 0. So, we can write for this special case d I mix will be equal to 1 minus y I divided by summation over j equal to 1, j not equal to I to n y I divided by d I j. So, this is equation number 8.7. Now, if we take this equation number 8.5 and the diffusion path length is L, then we can integrate this equation. So, we will have n I integral 0 to L dx will be equal to minus C d I mix integral y I 0 to y I L dy I divided by 1 minus y I. So, from this we can obtain n I is equal to C d I mix by L ln 1 minus y I L divided by 1 minus y I 0. This is equation 8.8. Now, let us consider a simple example. Carbon dioxide is diffusing through a mixture of nitrogen and hydrogen at 300 Kelvin temperature and 100 kilopascal total pressure. At one location, the partial pressure of CO2, nitrogen and hydrogen are 40 kilopascal, 50 kilopascal and 10 kilopascal respectively, and at another locations these components CO2 is 10 kilopascal, nitrogen is 75 kilopascal and hydrogen is 15 kilopascal. The distance between these three locations is 3 millimeter. The diffusivity values are given. This CO2 nitrogen is 1.5 into 10 raised to minus 5 meter square per second. This CO2 hydrogen is 7 into 10 to the power minus 5 meter square per second, and D N2 hydrogen is 8 into 10 to the power minus 5 meter square per second at the respective temperature and pressure. Calculate the flux of carbon dioxide. Now, we know NCO2, we have to calculate C d CO2 mix divided by L into ln 1 minus y CO2 L by 1 minus y CO2 O 0. So, C is equal to P T by R T. So, P is 100 kilopascal into 10 to the power 2 Pascal, and R T is given, R is 8314 meter cube Pascal per k mole Kelvin, and into 300 Kelvin temperature. So, it is 0.0401 k mole per meter cube. Now, this CO2 mix, since only component CO2 is diffusing and all other component are stagnant. So, we consider this DI mix, this equation will be valid 1 minus y CO2 by y N2 by d CO2 N2 plus y H2 by d CO2 H2. So, which will be equal to 1 minus 0.4 divided by at location 1 divided by 0.5 for nitrogen divided by 1.5 into 10 to the power minus 5 plus 0.1 divided by 7 into 10 to the power minus 5. So, this is 1.73 into 10 to the power minus 5 meter square per second. L is given, which is 3 millimeter is equal to 0.003 meter, and y CO2 naught is 0.4 and y CO2 L is 0.1. So, the flux N CO2 we can calculate 0.0401 k mole per meter cube into 1.73 into 10 to the power minus 5 meter square per second divided by 0.003 meter into ln 1 minus 0.1 divided by 1 minus 0.4. So, this will give around 9.37 into 10 to the power minus 5 k mole per meter square second. So, now we will consider diffusivity in solids. The diffusivity in solids is relatively less compared to the other two phases like diffusivity in gases and in liquids. From liquids it will be around 1000 times less, and from compared to the gases it is around 10,000 times less. And diffusivity values is important for catalysis and it is also important for metallurgical application, drying, adsorption, and also membrane separation. So, as we have seen, the diffusivity simple in the case of gases and liquids, it is not as simple as in case of the solids. The diffusion in solids we can broadly classify into two different categories. One is diffusion follow Fick's law. In this case, the structure of the solid is not important. Of solids is not important. And the second case is diffusion in porous solids. Diffusion in porous solids, where structure solids is important. So, first let us consider the diffusion follow Fick's law. In this case, the phenomena is like this: the components first dissolve in the solids and then it diffuse. So, the mechanism in this case is first the solute dissolve in solids and form homogeneous solution and then it diffuse. From high to low pressure side. And also when it dissolves from the solution, it obeys Henry's law. The diffusivity can be expressed by Arrhenius relation type in case of polymers and other solids, where it forms the homogeneous solutions, particularly in polymers. DAB we can define denote e to the power minus Hd by RT, where Hd is the energy of activation and D naught is a constant, and particularly for permanent gases the diffusivity values is approximately 10 to the power minus 10 meter square per second. Now, if the diffusivity is independent of concentration and the bulk flow, then steady state molar flux in the x directions we can derive by Fick's law. Na will be minus dAb dCA dx, where dAb is the diffusivity of component A through the solids. For a slab geometry, we can write, if we integrate the thickness of L of the slab, so it will be dAb Ca1 minus Ca2 divided by L, where Ca and Ca2 are the concentration at two different locations. For other solid geometry, this we can write W will be Na S average, which is equal to dAb S average Ca1 minus Ca2 by L. S average is the average cross section for diffusion. Section for diffusion. Now, diffusion coefficient in the solids is not depend on the pressure on the surface of the solids, which is outside on the surface of the solids. For example, if CO2 is diffusing through a rubber or any polymer materials, the diffusivity or diffusion coefficient would be independent on the partial pressure of CO2 on the surface. But the solubility of CO2 into the rubber or into the polymer will depend on the partial pressure of CO2 in the surface, or it is directly proportional. So, the solubility and the concentration we can directly relate with Ca. The concentration of a solute in the solid can be defined by solubility meter cube STP meter cube solid into atmosphere divided by 22.414 meter cube STP per k mole A into partial pressure of A in atmosphere, which will be S P A by 22.414 k mole A by meter cube solid. Now, let us take an example. The CO2 is diffusing through a polyvinyl alcohol membrane of 200 micron thickness at 70 degree centigrade and at 10 kilopascal partial pressure. The pressure of CO2 on the sweep side of the membrane is assumed as 0. The solubility of CO2 in the polyvinyl alcohol is given, and the diffusivity of DAB is also given at the temperature. Calculate the steady state flux. So, we can calculate CO2 at 1 in one side, that is the feed side, will be S P CO2 by 22.414 is equal to 0.007 into 0.1 by 22.414 is equal to 3.123 into 10 to the power minus 5 k mole CO2 per meter cube solid. Now, CO2 at 2, that is on the sweep side, is taken as 0, assumed as 0, and L is given as 200 micron, which is 2 into 10 to the power minus 4 meter. So, we can calculate flux in CO2 will be DAB C CO2 1 C CO2 at 2 divided by L, which is equal to 5 into 10 to the power minus 10 into 3.123 into 10 to the power minus 5 minus 0 divided by 2 into 10 to the power minus 4. So, it will be 7.81 into 10 to the power minus 11 k mole CO2 per meter square second. Now, let us consider diffusion in porous solids. So, if we consider porous solids, then the structure of the pores is very important, and this is particularly for catalytic reactor, where we can have the diffusivity inside the pore or adsorbed surface on the catalyst. So, if we consider pore diffusion, then at low pressure the collisions of the gas molecules will be less and the mean free path of the traveling molecules will be higher. So, pore diffusion, first we will consider pore diffusion. So, if the mean free path of the molecules at low pressure are higher than the diameter of the passage, in that case there will be a collisions between the molecule and the pore wall, and that will be very significant amount, and the diffusion occurs due to these collisions is known as the Knudsen diffusion, and this occurs when the pore size below 50 nanometer, and very much important for intra particle diffusion. So, the simple equations can be derived for the Knudsen diffusivity as proposed based on the kinetic theory of the gases is dk is equal to 2 by third R P into V average. So, R P is radius of pore and V average is the average velocity of the molecule, and this V average we can obtain from the kinetic theory of gases is 8 R T by pi m to the power half, where T is the temperature in Kelvin and m is the molecular weight. Now, the Knudsen diffusivity can be obtained similar to the Fick's law, J k will be minus d k d C A dx is equal to minus d k by R T d P A dx. Now, let us take very simple examples. CO2 is diffusing through a pore of catalyst at 400 Kelvin. The diameter of the pore is 50 angstrom. Calculate the Knudsen diffusivity of CO2. The given values are R P is 50 into 10 to the power minus 8 centimeter, R is equal to 82.1 centimeter cube atmosphere per gram mole Kelvin. 1 atmosphere is equal to 1.013 into 10 to the power 6 gram centimeter per second square per centimeter square, and T is given 400 Kelvin and m is given which is 44. So, dk will be 2 by 3 into 50 into 10 raised to minus 8 multiplied by 8 into 8.21 into 1.013 10 to the power 6 into 400 divided by pi into 44 to the power half. So, this will give you around 0.0146 centimeter square per second. Now, the surface diffusion, this is particularly important when the adsorbed molecules on the surface are diffused due to the concentration gradient. If the fractional coverage on the surface is less than unity, in that case some molecules which have higher energy can jump to the vacant sites or empty sites, and this mechanism is known as the hopping mechanism, and the flux due to the surface diffusion can be represented by Fick's law, which is J s is equal to minus d s d C s dx, where d s is the surface diffusion constant in meter square per second, and C s is the surface concentration in k mole per meter square. This is end of lecture 8 of module 1. After this, we will start with the lecture on module 2, that is on mass transfer coefficients. Thank you.